Usually when we talk about traditional cybersecurity, there's this underlying expectation of just rigid, inflexible rules.
Oh,
Like,
absolutely.
it's a lot like building a medieval fortress. You construct this massive stone wall, you dig a deep moat, you write a firewall rule,
Right.
and the system just looks at an incoming packet of data and literally says, blocked, you don't match the signature.
Mm.
It's entirely deterministic. The logic is just totally binary.
Yeah, and I mean, that predictable nature is what the whole industry has relied on for decades.
Exactly.
We design systems to follow the exact instructions we wrote, line by line, without any ambiguity whatsoever.
Right. If X happens, do Y.
Exactly. If X happens, execute Y. The perimeter was clearly defined.
But then you step into the world of artificial intelligence and cybersecurity, and suddenly that comforting rule book is just completely thrown out the window.
Oh, totally out the window.
We're looking at a defensive landscape that is like learning, evolving, and making probabilistic decisions completely on its own.
Yeah, because you're stepping onto a dynamic, shifting battleground now. You really can't secure a probabilistic, evolving intelligence using the exact same static mindset you use to, configure a basic network router.
Right, it just doesn't work.
It requires a completely different architectural approach because the asset you're actually trying to protect is effectively a black box that rewrites its own logic over time.
Okay, let's unpack this. Because traditional security is basically a bouncer with a strict VIP list, right?
Analogy, yeah.
If your name isn't perfectly matched on that clipboard, you do not get in. But AI security, it's more like a highly trained detective who reads subtle patterns, spotting a fake ID just by the way the person is sweating or, the cadence of their walk.
I like that, yeah.
And that is why today, learner, we are throwing out the medieval rulebook. We're taking the massive stack of CompTIA SecAI plus study materials, the MITRE Atlas threat landscape, the SAIL framework, and the OWASP guides.
That is a lot of material.
It is, and we're distilling all of it into a specialized, highly actionable masterclass. We are mapping out the ultimate roadmap of the AI lifecycle to prepare you for the SecAI Plus certification.
Which is huge. Our mission today is to transform you from a traditional security thinker into a true AI security architect.
Yes.
Because to secure a probabilistic system, we can't just, build a wall at the very end of the process. We have to secure the entire journey the AI takes to come to life.
From the very beginning.
Right. From the initial business planning all the way to its ongoing maintenance in a live, messy enterprise environment.
And we're going to culminate this entire deep dive with an immersive, scenario-based tabletop exercise to really test everything you've learned. So let's start at the very beginning of the life cycle.
Phase 1.
Right. Before our AI detective can actually solve a case, they need jurisdiction and they need evidence, which means aligning business goals and collecting the right data before a single line of code is ever written.
Yeah, and this is the core principle of Secure by Design, which is just foundational to the SAIL framework.
And SAIL stands for the Secure AI Lifecycle, right?
Exactly. Secure AI Lifecycle. Legal, compliance, and cyber teams must be integrated into the project on day one.
Day one. Not as an afterthought.
Never as an afterthought.
Yeah.
Let's say your organization's building an audio AI model to authenticate users based on their voice.
Okay. Pretty common use case.
Right. But if you collect massive amounts of audio data that legally belongs to a third party or violates privacy laws, you can't just casually hit delete on that data from the model later.
Because the model already learned from it.
Exactly. The weights have already shifted. It is infinitely cheaper to have a compliance officer flag that data set as restricted in the planning phase than it is to burn the entire model down after you've spent, millions of dollars on GPU compute.
Wow, yeah. Which naturally leads us right into how we actually gather that evidence. When we start collecting data, the ultimate proactive defense is just data minimization.
Yes.
Cut the liability off right at the source. If you're building a predictive maintenance model for factory equipment, you absolutely need the machine temperatures.
Of course.
You need the vibration logs, but you do not need the personal home addresses of the machine operators.
No, why would you? And the stakes in this early stage are massive. We see this documented super clearly in the MITRE Atlas framework.
ATLA, meaning the adversarial threat landscape for AI systems?
Right, which operates like the Rosetta Stone for mapping AI vulnerabilities.
Yeah.
They document this incredible real-world case study where an adversarial attack on a foreign tax authority's facial recognition system resulted in a $77 million loss.
Wait, 77 million?
77 million. And that happened because the system was manipulated by threat actors who understood exactly how the model processed its inputs.
Wow.
Threat modeling and business alignment at the very start are what prevent those kinds of catastrophic architectural failures.
But wait, I have a question here. If large language models, LLMs, derive their incredible conversational nuance by training on billions of unstructured, messy web pages, aren't we basically forced to ingest hidden risks and buried secrets by design? Like, how do we balance data minimization with an AI's inherent need for these massive, chaotic data sets?
Well, this raises an important question, and it really highlights the core paradox of modern machine learning. To build those capable, nuanced models, we absolutely must ingest that, quote-unquote, messy bedroom of internet data.
Right, we have to have it.
We're forced to accept the inherent risk of unstructured data. But that exact necessity pushes us into implementing rigorous active defense mechanisms in the very next stages of the life cycle.
The sanitization and development passes.
Exactly.
Because we collected a messy bedroom of data, we have to meticulously clean it before it becomes the model's brain. Now, data cleansing sounds like, I don't know, basic proofreading, but in AI security, it's a critical defensive mechanism.
Oh, it's life or death for the model.
Right.
Attackers play the long game. They will intentionally plant landmines in your raw data.
The mind's like, what?
Imagine a malicious actor hiding prompt injection attacks, which are essentially rogue commands deep inside years-old customer support chat logs or public forum posts.
Oh, wow. So they just leave it there for years.
Yeah. They're banking on the fact that one day your company will scrape those archives to train an internal AI. Data cleansing is the active process of scanning for and stripping out those malicious payloads before the neural network ever digests them.
And once that data is actually clean, we have to guarantee it stays pristine using cryptographic hashes, which introduces something called the avalanche effect. Let's say you have a massive data set of training images, right? We assign a unique digital fingerprint, like a SHA-256 hash, to that data set.
Okay.
If an attacker manages to alter a single microscopic pixel in just one training image to subtly poison your model, the avalanche effect ensures that the newly calculated hash doesn't just change slightly.
It completely scrambles.
Exactly. It produces a radically different string of characters. That massive mathematical shift breaks the digital tamper evidence seal, and your security systems instantly quarantine the file.
It's brilliant. That cryptographic seal protects our raw material, but then we feed that material into the development phase. And when we utilize deep learning, we're no longer relying on human-engineered features.
Right. It's totally autonomous.
A deep neural network utilizes hidden layers to stream raw byte streams and figure out the complex patterns entirely on its own. It sacrifices human explainability to achieve immense power.
And that lack of explainability leads to massive vulnerabilities. Like we start seeing supply chain compromises, right? Like model confusion.
Oh, model confusion is terrifying.
Yeah. A developer might be working on an audio AI project and decide to call a simple from pre-trained function to download model weights from a public repository like Hugging Face.
Happens all the time.
They think they are downloading a helpful pre-trained audio processing tool, but those weights have been maliciously altered. And suddenly they have triggered remote code execution directly on their own enterprise servers.
It's a huge blind spot.
But here's where it gets really interesting. If the math driving deep learning is so incredibly complex that it operates like a black box,
Yeah.
like if it is alien even to the engineers who created it, how can we possibly secure the development phase against threats we literally cannot perceive?
By accepting a really hard truth.
Yeah.
We cannot blindly trust the model's internal logic.
You just can't.
We can only trust how it reacts when we subject it to extreme stress testing in a sandbox environment. Before this asset ever touches the live internet, we have to try and break it.
Right.
We evaluate and validate. High accuracy on a practice test is dangerously misleading. We have to explicitly test for overfitting, which is, what happens when a model, it's essentially memorizes the training data perfectly, but fails miserably the second it encounters new, unseen data in the real world.
Like cramming for a test, but not actually learning the subject.
Exactly.
We also have to perform temporal validation. Like, did our security AI actually learn the fundamental mathematical patterns of a cyber attack? Or did it just memorize the specific historical dates of old, patched breaches?
Right. Is it predicting the future or memorizing the past?
Exactly. And we have to actively attack our own creation using red teaming and adversarial examples. We rely on mathematical metrics, like the clever score, to calculate exactly how much an attacker needs to alter an input before the AI gets confused and makes a mistake.
And evasion attacks are a perfect example of why this testing is so vital. According to MITRE Atlas, a threat actor can alter a few specific pixels in an image of a 45-mile-per-hour speed limit sign.
Okay.
The alteration is mathematically calculated to disrupt the machine vision algorithm, right? Yet it remains completely invisible to the human eye.
Wait, really? Invisible?
Totally invisible. To a person, it looks like a normal speed limit sign. But the neural network will confidently, 100%, classify it as a yield sign.
But if these adversarial pixel changes are completely invisible to the human eye, how is a human security analyst supposed to validate the model against a threat they literally cannot see?
Well, you fight AI with AI. You
Ah.
systematically generate those invisible adversarial examples synthetically. You feed them into your own model, document exactly where the model's logic breaks down, and then you use those very failures as a new training data set.
So you're forcing it to learn its own blind spots.
Exactly. You force the model to learn what the invisible noise looks like. Only after it proves its robustness does it actually earn the right to move into deployment and integration.
And the deployment phase is hostile. The open internet requires strict container hygiene. We're talking about using Docker, ensuring you use minimal base images so there are no unnecessary system libraries for an attacker to exploit.
Critical.
And never, ever running the application as root.
Never.
We also have to completely rethink how we prevent abuse. You can't just use IP-based rate limiting anymore.
No, that's useless now.
If you limit queries by IP address, a botnet will just rotate through thousands of different IP addresses and entirely exhaust your model's wildly expensive GPU resources.
Yeah, your cloud bill will be astronomical.
Right. You have to use token-based rate limiting, which ties directly to authenticated user sessions.
Furthermore, you really cannot rely on the LLM to police itself. You must construct guardrails.
Right, outside the model.
Exactly. These are hard, deterministic architectural layers sitting entirely outside the core language model. They intercept and evaluate user inputs, blocking prompt injections before the model even has a chance to process the text.
But surviving deployment is just the beginning, isn't it? The environment around the model constantly changes. A perfectly secure model today becomes a massive liability tomorrow.
Because of concept drift. It's the silent killer in ongoing maintenance.
Concept drift.
Yeah, if you train an AI model to detect phishing emails in January, by July, it's essentially looking for last season's fashion.
Right.
Attacker tactics constantly shift. The baseline reality changes. This dictates that scheduled retraining isn't just a nice upgrade, it is a fundamental security requirement.
You also need continuous auditing pipelines, like hallucination auditing catches the AI fabricating facts, which happens because fundamentally an LLM is just calculating the next most probable word. It's not referencing a database of truth.
Right, it's just guessing really, really well.
Exactly. You also have bias and fairness auditing. For instance, catching a model that automatically associates the word doctor with masculine pronouns.
Which is a huge issue.
Yeah, and that happens because of historical vector clustering in the training data, where those words were mathematically grouped close together in legacy texts.
Crucially, you also have to implement human-in-the-loop architectures.
Okay, how does that work?
You constantly monitor the model's probabilistic confidence levels. If an AI is reviewing a critical medical diagnosis or a highly sensitive financial transaction and its internal mathematical certainty drops below 85%.
It shouldn't guess.
Exactly. It shouldn't guess. It automatically kicks that specific decision to a human queue for manual review.
So what does this all mean? If a model degrades constantly due to concept drift, isn't continuous maintenance just treating the symptom? Like, at what point is the model just broken beyond repair?
Well, what's fascinating here is that an AI model is never truly finished. It is a living, breathing digital asset.
A living asset.
Yeah. The SAIL framework demands continuous looping iteration, precisely because the environment the model operates within is continuous. Treating the symptom is the only cure when the disease is a constantly changing reality.
All right, learner. We've decoded the theory. We've mapped the terrain. Now it is time to put you in the hot seat.
Oh, here we go.
We're transitioning into the SecAI Plus Masterclass tabletop exercise. We're going to throw you into 8 rapid-fire enterprise scenarios covering all 8 domains of the AI lifecycle.
Get ready.
We will tackle 32 specific concepts you must master. Imagine you are the lead security architect for a massive global enterprise. Are you ready? Let's dive in.
Right, learner. Scenario block 1, the foundational architecture. You are taking over an enterprise that has only ever built traditional software. Your executives want to know what framework will unify your security practices across both the AI lifecycle and the traditional software development lifecycle. What framework are you implementing?
You're implementing the SAIL framework. And when the board asks why your traditional deterministic security tools keep failing to protect the new AI assets, what do you tell them? You explain that AI makes dynamic, probabilistic decisions. It doesn't follow rigid, static rules.
Exactly. You mandate that security must be woven into the architecture from day one, that foundational philosophy known as secure by design.
Always.
Now for your first performance-based challenge, learner. You have a whiteboard, and you must map security controls to their correct lifecycle phases.
Okay, marker in hand.
Where do you place container hygiene, threat modeling, and adversarial training?
You place threat modeling in the early planning phase, adversarial training belongs in the test and evaluation phase, and container hygiene goes straight into deployment. Boom.
Nailed it. Moving to scenario block 2, business alignment. You're launching a new AI project. When exactly do you demand that legal compliance and cybersecurity teams be integrated?
Day 1, during the planning and business alignment phase.
And let's say your executives try to draft corporate AI policies that dictate specific algorithmic hyperparameters.
You stop them right there. You clarified that the primary purpose of corporate AI policies in the alignment phase is dictating approved tools, data handling, and cloud usage, not doing the data scientist job for them.
Right. And to assess the risks against this new project, you run an exercise mapping out specific adversarial tactics against AI models. Which framework are you using to guide this?
You are using the MITRE ALS framework.
Perfect. And for your next performance-based challenge, you're sitting in a room leading a session asking your team, what are our AI's assets and who could realistically attack it? What methodology are you actively applying?
You are actively applying proactive architecture defense, otherwise known as threat modeling.
Spot on. Scenario block 3, data collection. You begin gathering the massive data sets required for the model. What is your ultimate proactive defense mechanism during this phase?
Data minimization. Cut the liability entirely by never collecting what you don't need.
And if a sister hospital in your network wants to integrate an external data set,
Before you allow it, you mandate they confirm the trustworthiness and authenticity of the sources regarding the privacy policies.
good. Now, to protect the privacy of the individuals in that data set, you apply a technique that groups individuals into broader categories, so the model still learns the useful patterns, but cannot expose any specific person. What is this called?
That is generalization or masking.
Okay, performance-based challenge time.
Bring it.
You're building a predictive maintenance model for factory equipment. You receive a raw data set containing equipment logs, machine temperatures, and the personal home addresses of the machine operators. What is your immediate non-negotiable action?
You drop the home addresses from the data pipeline entirely before the collection is ever finalized.
Absolutely. Scenario block 4, data preparation. Before the data is ingested, you mandate rigorous data cleansing. Defensively speaking, why?
Because you are actively stripping out malicious inputs like SQL injections or prompt injections that threat actors have hidden in free text fields.
And to ensure the data set is never altered behind your back after cleansing, what technical mechanism do you implement?
Cryptographic hashes or checksums.
And if an attacker manages to alter a single pixel in an image to bypass your checks, what happens to that hash?
The avalanche effect triggers, causing the newly calculated hash to be radically, fundamentally different, instantly alerting your security operations center.
Great. Your performance challenge for this block. You need to replace highly sensitive text data with unique identifiers while maintaining the data's utility for the model. You are looking at 2 options, perturbation and tokenization. Which do you configure and why?
You must configure tokenization. Tokenization swaps the sensitive text string with a meaningless reference ID. Perturbation doesn't work for text. It is used to add random statistical noise to numerical data.
Exactly. Scenario block 5, development and selection. Your data scientists introduce a model that analyzes raw byte streams to detect zero-day malware without any manual human feature engineering. What AI approach is this?
That is deep learning.
But shortly after, you detect an attack. A threat actor is repeatedly querying your AI with tiny fragments of medical records, analyzing the model's probabilistic confidence outputs and adjusting their queries until the neural network accidentally reconstructs and spits out a specific patient's confidential file. What attack is this?
That is model inversion. The attacker is reverse engineering the private training data.
Following this, a junior developer attempts to call a from pre-trained function to load model weights directly from a public hub. What catastrophic risk are they introducing?
Model confusion, resulting in a major AI supply chain compromise.
Now for your performance-based challenge. During the development phase, an insider threat slightly alters your model's internal parameters to change its behavior. What specific attack has occurred, and how do you mitigate it?
That is model poisoning, and you mitigate it by enforcing strict access controls and securing your supply chain management within the development environment.
Well done. Scenario block 6. Evaluation and validation. Your model looks incredibly impressive during training, scoring perfectly, but fails miserably the second it analyzes real-world, unseen data. What has occurred?
Overfitting. It just memorized the practice test.
To prove the model actually understands cyber threats and didn't just memorize specific dates of historical breaches, what specific validation do you run?
Temporal validation.
During red teaming, an attacker simulates altering invisible audio frequencies in a voice command, so the AI transcribes a malicious instruction instead of the user's actual words. What type of attack is being simulated?
An evasion attack.
Your performance challenge for this phase. You must empirically measure a model's robustness. You have access to the Kermes Resumes dataset. What exact steps do you take to perform adversarial training?
All right, 3 steps. First, you programmatically produce adversarial examples of the Kermes resumes. Second, you feed them into the model to compute exactly how often the attack succeeds. Third, you take those successful adversarial examples and use them as a brand new training dataset to immunize the model.
Perfect 3-step process. Scenario block 7. Deployment and integration. Your model is live. To prevent an attacker from bypassing your chatbot's core logic via prompt injection, what hard architectural layer do you place entirely outside the core language model?
Runtime guardrails.
Immediately, you notice an attacker is burning your expensive GPU compute for free by utilizing a botnet to rotate through thousands of different IP addresses. Why did your IP-based rate limiting fail to stop them?
Because you did not implement token-based rate limiting tied directly to authenticated user sessions.
To protect the underlying server infrastructure, what practice ensures the model only has the absolute minimum system libraries required to run?
Containerization using minimal base images.
Your performance challenge. You are integrating an LLM into an external-facing public website. How do you mitigate the risk of the model's output containing malicious JavaScript that eventually executes on the end user's browser?
You must apply conventional software security controls, specifically output encoding, before rendering any of the model's text back to the user.
Finally, scenario block 8. Monitoring and maintenance. A retail company in your portfolio asks why they must spend resources retraining their product recommendation model every single month. What is your technical justification?
They must combat concept drift because consumer behavior and the baseline reality of the world change constantly over time.
A customer support bot confidently gives a user a highly detailed answer referencing company policies that absolutely do not exist. What type of audit will catch this specific behavior?
Hallucination auditing.
A hospital's AI diagnostic tool routes uncertain predictions directly to a human doctor's queue whenever its statistical certainty drops below 85%. What core design principle is this?
Human in the loop relying on confidence level monitoring.
Your final performance-based challenge, learner. During an audit, you discover your AI logs contain full transcripts of user interactions stored in plain text, completely violating privacy policies. What specific control must you configure in your monitoring pipeline?
You must implement log sanitization using data loss prevention pipelines to actively scrub all personally identifiable information from context windows before they are ever written to disk.
And that concludes the tabletop exercise. If you kept pace with that, learner, you are actively thinking like a senior AI security professional. Passing the SecAI Plus certification is not about memorizing buzzwords. It's about dynamically applying this exact architectural logic to actual breathing enterprise environments.
Exactly. You survived the deep dive. Be proud of that. But as we wrap up, I want to leave you, our learner, with one final provocative thought straight from the source material.
Let's hear it.
We started this whole conversation by talking about how traditional security was a static fortress and AI is a shifting, probabilistic battleground. If we connect this to the bigger picture, As these AI systems become increasingly capable of automatically threat modeling their own code, autonomously deploying infrastructure patches, and responding to AI-generated attacks at machine speed.
We have to ask ourselves a huge question. Are we rapidly approaching a future where cybersecurity is entirely machine versus machine?
And if we actually reach that point and we remove human analysts completely out of the loop,
Yeah.
who is ultimately responsible when the machine makes the wrong call?
That is the million-dollar question.
Think about that shifting battleground. Keep questioning the black box, keep exploring the architecture, and remember that true learning only happens when knowledge is applied. See you next time on The Deep Dive.